Anyway, so I guess going back to inflation, sort of the idea that we were looking at is sort of bringing inflation sort of at TeV scales, and maybe we want to probe these things at sort of LHC scales. So the basic, so maybe a motivation behind this in some sense is from scales of physics. So the nice thing is we can bring inflation to the TeV scale. Maybe in principle there's one fundamental scale in the universe, which is the TeV scale. And in this model, it has the advantage of also solving the graceful exit for old inflation. We do this in this model. There's no rolling field, and then the nice thing about TeV scales is stuff that you can search at colliders, and you can relate sort of cosmological parameters to particle physics parameters that you could probe at, let's say, like C, for instance. And then as a point, it's actually what's nice about this model is it's technically natural in the same way that QCD is. So the basic scenario is that the universe starts off hot, and radiation dominated, and therefore you sort of sit at the symmetric minimum of the scale of potential. As the universe cools, the true vacuum appears, but you're still sort of isolated at the symmetric minimum. And so in our toy model, we sort of set this at 1 TeV. The universe then supercools, generating a sufficient number of U-folds to solve the standard cosmological problem, the flatness and horizon problem. But the universe then sort of sits in the false vacuum and never transitions. And this goes back to what the graceful exit problem, or the initial problem that Guth and Weinberg had shown. So what we really require is a way to transition out of the false vacuum. And so we just remind you as the universe is expanding, the temperature is exponentially falling. And then at some critical temperature, we have a non-abelian engaged group which becomes strongly coupled. And in this case where we have a series of quark-like fermions, they get a VEV, and that generates a tadpole term in potential. And then the tadpole term removes the barrier, and the universe then actually rapidly transitions to the true vacuum. In this picture, you also need a way to generate density perturbations. And so we introduce a spectator field, which then generates these perturbations, similar to a curvaton model. And so in principle, it can also produce some interesting and now not so interesting isocurvature or non-Gaussian perturbations. So we're going to talk a little bit about new and old inflation versus new inflation, I suppose. I'll then lay down what the particle physics model that we wrote out to be. I'll show you that the false vacuum is quite stable, how you then end inflation, reheating perturbations, and everything else. So again, the universe sits in this false vacuum, you inflate, you solve the flatness and horizon problem, and then you tunnel to the true vacuum. So that was old inflation. But as I said, the model fails because there's no graceful exit, which is famously related to the Swiss cheese problem. For inflation, it requires, so you percolate these, you generate bubbles of true vacuum, and then these bubbles have to sort of meet each other, and then percolate, and then that would sort of, then the universe can transition from the false vacuum to the true vacuum. You can rephrase that into how much inflation could you get in a stage, and in this instance, you could only constrain to get a third of an E-fold. So you're sort of left with a difficult situation. Either you can solve the horizon flatness problem, or you never end inflation. So that was sort of the problem with old inflation. So the solution to this was sort of new inflation, for instance, where you generate a graceful exit just through scalar dynamics, just as at some point inflation ends. So there are various models to do that. Instead, one could also in principle use a thermal effect, and this was sort of done by thermal inflation. But in this instance, that model does not solve the cosmological problems. So in our model, it's sort of the standard model redux. So you have Lagrangian in the standard model, but without the weak and electromagnetic components. And then you're left purely with a tidal QCD-like fermions charged under hitting U1. So that'd be like electromagnetism, and the QCD-like non-abelian gauge group. And then the Higgs sector or inflaton is a Higgs model, which is also the charge from the 2-1. And we take this to be a Coleman-Weinberg potential. So here's the effective potential. The first term is stabilizes the false vacuum to arbitrarily low temperatures. The second one is just the Coleman-Weinberg potential, which generates your true vacuum state. And then you can see the U power term, which then generates an inflation. In sort of our toy model, we set the VAD to about 10 TeV, and then sort of order 1 parameters for your coefficients. And we set the scale of inflation to be 1 TeV. Could be higher, could be a little lower. So in this picture, you can ask which instanton should you consider, and you find that the O3 thermal instanton is actually dominant. All other instantons are subdominant. And at that point, then you just have to then consider what are your probabilities of transitioning. Again, if you go back, there's a criteria between basically the tunneling rate over the size of the universe, and you can check whether or not your tunneling rate is large or small in that limit. And you find it's much, much, much smaller. So you're stuck in the false vacuum. So again, so in this model, hence no tunneling, sorry. So in this model, again, you have sort of TeV scales. And so you can ask, again, initially the universe is hot, so it's cooling down. Inflation then begins at around 300 GeV. Again, it's just the temperature falls as the inverse to the scale factor. So you're exponentially driving down the temperature of the universe. And sort of after 30 e-folds inflation, the temperature of the universe has actually dropped to about 10 to the minus 2 eV. So in that limit, we're at 30 e-folds at TeV scales. You can then solve this standard cosmological problem, the flatness horizon problem. And then we can just set this point to be our critical temperature at 10 to the minus 2. So at the critical temperature, as in like QCD, your hidden gauge group becomes strongly coupled. At that point, your quarks generate a VAV, which generates a tadpole term. And so you can rewrite the effective potential of this new term. You can replace the quarks with this effective term on the left with a tadpole term. And so you can go through and rewrite your potential, and then you find at what temperature does the barrier go away, and precisely in just taking sort of order 1 parameters for your quarks, at the critical temperature the barrier will be removed. And so once you remove the barrier, then the inflaton quickly goes to the minimum potential, converting the vacuum energy into scalar particles, which then can actually decay into standard model particles. And so in that case, you can consider if you have to connect some hidden sector to the standard model, there's 3 ways to do that. Either with a scalar or vector, either through a scalar interaction, vector, or scalar fermion type of interaction. I'm going to focus on the vector or kinetic mixing. In this case, the decay is through a Z boson. And then if you put in some reasonable parameters that I used before, you find that the universe instantaneously repeats. You can then also, something you usually don't have to worry about when you do inflationary models is avoiding collider constraints from LHC. But the parameters that are chosen for the time being, one should be able to avoid the constraints coming from Z prime searches. And so then so now that you've fixed the standard cosmology, you also then have to generate density perturbations. But there's sort of a problem is that with standard adiabatic density perturbations are suppressed by the finite temperature. And so you need to come up with an additional way to do that. So in 1990, Silverman and Malaric showed that if, let's say, you have a matter component which has an isocurvature perturbation, if that field then decays into radiation, you can then generate a real adiabatic density perturbation. So in the same way that one can then do this with sort of an axion type potential, you introduce a pseudoscalar with U1 symmetry, which is broken, and the field at the angular variable, and the field then is the angular variable of the hat. Again, the spontaneous symmetry breaking scale just sets the width of the hat, and then you have some sort of explicit breaking term that then gives you your height. So the basic sort of picture that we have is that during inflation, the mass and the decay constant are small, and at the end of inflation, so in the beginning of inflation around 10 to the minus 1 eV, at the end of inflation, we can couple the inflaton with this with a Maxine hat type potential, and then that can acquire a large VEV. And in a case where you consider this to be something called a constrained insynchrone, then you find that the mass is also proportionate to your VEV. So at the end of inflation, initially the VEV is small, the mass is small, but at the end of inflation, the mass becomes large and the VEV becomes large. And so with that, you sort of can then match on to your standard cosmology, or at least when you match from the CB. So to get the right spectrum of perturbations, both the mass and the breaking scale, the spontaneous breaking scale, are small during inflation. But then at the end of inflation, you require that the spectator field should become an interesting part of the energy density universe, and that requires the mass and the field value to become large, which is precisely what we have by coupling both the inflaton with the spectator field. So, sort of a take-away message. The idea is that one can actually generate a successful period of inflation, which solves the standard cosmological problems and matches onto the cosmological data. I think that's what any inflaton, any inflationary model should do. And I think the nice thing about this model is it does not need to take place at high scale, and again, sort of TeV scale. So if you're worried about the hierarchy problem, you kind of get rid of it by putting everything at one very low scale. And the nice thing is that I think from sort of a model building perspective and a particle physics perspective, you can make a relationship between both sort of your cosmological parameters and things that you find in the lab. So in some sense, there's a predictive power in this, that this model makes a strict connection between the spectrum of the type of particles you have and so for instance, what is NS supposed to be? So there's an interesting prediction that you would have a certain type of potential that you find, and they would have certain parameters, and they would match it. And I think that's actually quite a powerful predictive power as a model, something you generally don't get with inflation. And then the other point about this is that I think to some degree the issue with inflation is how do you maintain inflation for so many e-folds, right? So the temperature exponentially drops. How do you have that exponential increase of the universe and then have that stop at the end? And so in the case of inflation, you have to make this potential extremely flat, right? So that's a sort of a fine-tuning problem. Here we get around this because we have an exponential change in our temperature, but our coupling constant only changes logarithmically with that, right? So so precisely what you would consider to be technically natural. And so that's the connection between this being sort of technically natural.